All right. Now we're going to do what I think is the only Physics C specific section that involves zero calculus. So technically, all my AP1 people can totally follow everything in here, just know it's not on the AP1 test. So we can actually go a step further with springs and look at combinations of them. So instead of just a spring and a mass, we could attach multiple springs to each other. And it turns out there's always a way to condense the springs into a mathematically equivalent spring. So it's complicated to look at multiple springs attached to one another, but it's easy to do with one spring. So we always will have a mathematical trick to collapse a series or parallel combination of springs into a single one. So we can always figure out how to write the system in terms of a Hooke's law equation, and then the number in front of the total displacement becomes our equivalent spring constant. Now, there are two ways that we could combine springs. We have parallel, which, as the name implies, looks like your two parallel lines. This is where the springs are attached side by side. And in this configuration, we will learn that you have the same displacement of each spring, but different forces. And what this results in is a bigger, more powerful spring constant. So doing springs in parallel creates a stronger overall spring, and we say it increases the equivalent spring constant. It will be larger than the springs individually. Then the other way you could connect two springs is called series or end to end. And we'll learn that series springs have the same force exerted on each other. We'll see that the first spring exerts the same force that the second spring does, which is exerts the same force as the overall network, but they have different stretches. And this actually results in a lower spring constant than any of the individual springs, creating a weaker overall spring with more extension. So let's start with the easy rule. In parallel, it is literally just addition. So what we're saying is that if you have two springs that are side by side in parallel, the system behaves mathematically the same as if you just crunch those springs into a single spring, holding the combined spring constant. And as a result, since it's just adding spring constants, the equivalent spring constant will be bigger than K1 and it will be bigger than K2 because we are just adding those together. And in parallel, each of these springs will share the same displacement because the attachment point is the same right here. So the springs have to stretch the same amount, but the forces won't be the same because if you're stretching springs the same distance, but you have different force constants, one spring will be harder to stretch than the other, so you'll get a bigger force from one versus the other. So, really, the reason why parallel creates a stronger spring is because for the same displacement, you're getting an extra force from that additional spring. So, you're getting an extra force for the same displacement. So, you're getting more newtons for the same centimeters, which is a bigger spring constant. So, let's do a derivation now. A block of mass m is attached to parallel springs. Assume that K1 is less than K2. So usually I try to denote my bigger spring constants as more compressed or bulkier looking. So let's draw the forces exerted on the block. So, of course, the block has weight. And this might be our first time of having multiple forces next to each other. Yeah, I think it is. So we always draw our forces side by side. Now you could just draw like a single spring force up, but I think it's best to split it here. So notice that spring 1 extended a bit, that'll supply a force, and spring 2 extended a bit, and that'll supply a force. And since the springs are extending the same distance, but K2 is a stronger spring, more of the force will be supplied by K2, the spring with constant K2. So when we do side by side, I'll do this. We have a force from spring 1, and then we also have a force from spring 2. So notice they are not going to be the same. But if I add up, I have 1, 2, 3 units up and 3 units down. The displacement of each spring will always be equal in parallel. Why is this true? Well, I said it on the other page. The attachment point is the same. So both springs are attached, their tops and bottoms are attached to the same spots at the same heights. So they gotta just act as a stretching unit due to the side by side definition. Like there's not a whole lot of justification you can do other than this is just what it means to be side by side. Block is attached to the end of each spring at the same time. The springs must extend the same distance. Now, what about the forces? Well, we already did the dirty work here with our free body diagram. So we know they stretch the same distance, but K2 is a stronger spring. So there will be more force exerted by spring 2 for a given extension, because you're pulling the springs down the same extension, but there is a larger spring constant for spring 2. Greater force constant means greater force for a given extension. All right, let's verify the rule for the effective spring constant for two springs in parallel. So to do this, we use what's called the total Hooke's law equation. So the total force exerted by the springs on the mass is equal to the equivalent spring constant times the total linear extension of the spring. So in this case, we have the same delta x, which means that delta x total is just delta x. There's no summing happening because if I break it down, it's just a single spring extending. We're not adding their stretches. And we have different forces. So the total force is going to be the force from spring 1 plus the force from spring 2. So now we can try to prove our rule. So the total force would be the two forces added together. Our equivalent spring constant is KEQ, and that would be delta X. And we do know what the force would be from each spring. The force from the first spring would be K1 times delta X1, or just delta X, sorry. And the second force would be K2 times that delta X. And everybody brought delta X to the party. So cancel, cancel, cancel. So we get the equivalent spring constant is just K1 plus K2. So now we got to talk about series. So parallels adding, what is series? Now, if you haven't had any exposure to electronics, this is going to look quite strange that this is somehow the series formula. This is how it's usually written in books, where the constants don't add, but the reciprocals of the constants add. But I like it in this form because this is how you type it into a calculator to solve. So, because again, -1 power means flip the fraction. So if I were to flip both of these sides, I could do that with a -1 power. Now, I said people with electronics exposure, this doesn't look that odd because this is actually the inverse of how objects called resistors add in series and parallel. So we'll see, this is a pretty common property in physics where if something adds via summation in parallel or series, the other parallel or series version would be the reciprocal. So this is a very common like binary we see. So something will add directly and the other one will add reciprocal rule. So this means that if we have two springs in series end to end like this, the equivalent spring constant follows this rule. And this is less easy to see from the formula, but it is true that this always guarantees a series spring constant is lower than any of the springs that go in. So you get a weaker spring than any of the individual springs in series. That is a really important thing to note. That is explicitly in the mechanics CED. I imagine that is something that gets tested quite frequently. So why is this true? Well, in series, each spring experiences the same force. We will justify this using Newton's third law. So if the same force is being applied to both springs, and that force is also being applied to the mass, you're getting more extension than you usually would for that force. So the addition of an extra spring in series gives you extra extension. So the same force is costing you extra extension, resulting in lower newtons per meter. So that's kind of our intuition there. All right, draw and label the forces exerted on the block. So once again, let's just keep it as our 3 tick marks. This seems to be my go-to. And then here, the spring force is just going to be a single one pointed up. Why is that? Because forces require contact. What spring is contacting M? Well, there's only a single spring. Technically, it's K2. We could call this like F spring 2, but we'll see that they're all actually the same. So there's only a single force exerted on M, and it is the force from K2. The magnitude of the force F exerted on each spring will always be equal in series. Justify this claim. So why is that true? The common argument, which I like it, I guess, would be to consider this little attachment point between the springs. So we know that this system is in equilibrium. We also know that both of these springs are stretching. So, due to that fact, we know that there will be forces both down and up on this point due to the stretching springs. Think of it like a tension. But if that point is just going to stay there at rest, all the forces must balance. So that's one way of thinking about why the forces are equal. I actually just like a Newton's third law approach. Might not be the most rigorous thing, but I've always just interpreted this as Newton's third law, where the springs are pulling on each other. So if you have two springs that are attached, they're pulling on each other. And any time two objects pull on each other, the forces are equal in magnitude and opposite in direction by Newton's third law. So the forces must be equal between the springs, meaning the forces are equal throughout the whole system. Right? At the point of attachment, the springs are pulling on one another. This force between the springs is equal and opposite by Newton's third law. Forces weren't equal, the contact point would accelerate and just not be in equilibrium. That was kind of the first argument. All right, what about the displacement of each spring? So once again, we have the light spring K1 and the bulky one that has a larger constant K2. Well, we said that this configuration is the same delta X. So, or sorry, no, bad. This configuration is the same force. So we have different delta X. So we know that we have to create the same force from each of these. So this creates some force, this creates some force. We have to make the same one. So if the force is the same, you need to extend the weaker spring further to get the same force. Because again, that spring constant tells you how much force you get per unit of extension. So if you extend the spring with a lower spring constant, you got to extend it further to get the same force that you would need to generate. So delta x1 would be larger. From that reason, forces exerted by each spring are equal by Newton's third law. This is common abbreviation. I don't know about doing it on the actual AP test. I'm sure you would get the benefit of the doubt, but I'm not telling you to do it. I just do it because I'm lazy. Thus, the spring with a greater force constant requires a lower extension for the same force, right? That means that x2 is less. I don't need to extend it as far to get the same force. All right, let's verify the series formula. So we always start from the same spot. Total force is equal to the equivalent spring constant times the total extension. So here we have the total force is the same as the force from the first spring, which is the same from the force from the second spring, which is just some value F. Then delta X total is not the same because each spring is adding an extension. So we have some sort of summation to do. So this allows us to substitute. So F total is just F times KEQ times delta X1 plus delta X2. Now, this isn't very helpful because we need to somehow get K's involved. And we know that the force F is the same. So we're going to actually eliminate the delta X's in terms of the forces because we know, for example, K1 delta X1 would be equal to the force F, which means that delta X1 could be written as F divided by K1. And a similar argument could be used to get us delta X2. And why we like this is because it gives us everything in terms of F. So therefore, everybody would have brought in F to the party, so we can cancel it and have something in terms of only K's. So we can now write this as F equals KEQ times F over K1 plus F over K2. And as promised, everybody brought F to the party. I don't know why my canceling was the wrong color there. So we would get 1 equals KEQ times 1 over K1 plus 1 over K2. So divide both sides by KEQ and we get the standard series form. 1 over KEQ is 1 over K1 plus 1 over K2. I think it's nice to derive these once. So I really see these as like kind of like niche multiple choice questions where you just have to apply this. They're usually qualitative, like a lot of comparing things with the series in parallel. So knowing that force is the same in series with different extensions, parallel extensions are the same with different forces. That's kind of more common. But just to conclude, we'll do a little maybe QQT. I mean, everything I do is a QQT. So, all right, so we have two configurations. We have 3 and 6K attached to the same mass, and we want to compare the total force, total displacement of each block, spring constant, and some extension ratios. Okay. So, first we want to compare the total forces exerted by the springs on the block in each scenario. So what does that mean? Well, our first block has mg down, so there must be a total force from the spring, and there's a total force from the springs up. Same thing over here. We have a force mg down, and then we have a total force from the springs up. So what we can conclude here is that in total, the forces exerted by the spring network must be the same in each case because we are just balancing the weight mg of the block. And then we want to compare the total displacement of the block in each configuration and justify our answer. So here's where we deal with some knowledge of series and parallel. So this is good just to memorize, just know this. So we have the same springs, we add them in series versus we add them in parallel, and I just said it backwards. We add them in parallel versus we add them in series. So what we know first is that in parallel, the spring constant gets bigger than the biggest constituent spring constant. So we know that KEQ here is actually larger than 6K. Yes, I know it's 9 because 3 plus 6 is 9, but we're just seeing how qualitative we can get. In configuration 2, we know that the equivalent spring constant is weaker than the weakest because springs get weaker in series, so it is less than 3K. So what does this tell us? This tells us that the spring constant in configuration 1 is larger than the spring constant in configuration 2. Because parallel makes a strong spring, series makes a weak spring. So we know that we have to supply the same force mg from each spring network. So each spring network must supply the same force mg. And we also know that force is being supplied by springs. So what is the extension? Well, the spring constant is larger for configuration 1, so we don't have to extend as far, right? If we have a really weak spring, really stretchy spring for K2, this is a much more stretchy configuration because it's a weaker spring constant. You got to go further for the same force, right? Spring constant increases in parallel, decreases in series. So Springs will extend by a lower amount in configuration due to the greater effective spring constant. I should have written in here that the force is the same, that they are creating the same force. All right, what is the equivalent spring constant? Well, configuration 1, easy, right? Because K in parallel is just going to be the sum of the spring constants. Wow, what a surprise. 3 plus 6 is 9. Now, configuration 2, you can choose to do this kind of however. There's a nice little shortcut I think we'll talk about. Also, just to save yourself, you know that like it's going to have units of k. So this is how I like to do the series computing, right? 1/3 plus 1/6 to the -1. You can check that this is just 2. This will be equal to 2k. And I know that that's right because I wrote this. I always pick 3 and 6 because they're a nice reciprocal. Another thing you can check is that the formula reduces to this if you actually work it out for two springs. So product over sum, you get 6 times 3, which is 18, divided by 6 plus 3, which is 9. That's another way of looking at it. But we do see that we get a larger than 6 spring constant for the parallel and a lower than 3 spring constant for the series. All right, and let's calculate the ratio. Delta x2 over delta x1. So we are interested in this fact, and we know we are creating the same force F, which is going to be equal to K times delta X. So that means that delta X is just going to be equal to F divided by K. Because we know that we are creating the same mg force. Maybe that's worth writing. That's why I didn't put subscripts in that F. So delta x2 divided by delta x1 is just going to be equal to F over K2 divided by F over K1. The forces divide out. So we get 1 over K2 divided by 1 over K1. We could write this as keep, change, flip. So this would be 1 over K2 times 1 over K1, or flip 1 over K1, so K1. So we get K1 over K2. We said that the spring constant in configuration 1 was 9K. The spring constant in configuration 2 was 2K. So we get 9 halves as our ratio. This is like the official way that some people prefer to do these ratio questions. This usually isn't my favorite style. I'm usually more of a multiplier person. If I were to show you how I would have personally done this with the multipliers, we can give ourselves a little space here. I would have said that I need to create the same force F. I would have said that F1 equals K1 times delta X1. So then my F2 would be K2 times delta X2. So scoot this over, make sure we can see it and read it. So I would have said that I know the forces are the same, so this is a times 1. And K2 is 2/9 as big as K1. Meaning to create the same force, X2 must be 9 halves as big to get that canceling. So that's how I would have done it. Symbol plugging and chugging won't do you wrong though. So is this consistent with our claim? Yes, it's consistent because delta x2 divided by delta x1, we said is equal to 9 halves, which is greater than 1. So delta x2 is larger than delta x1, as expected. So that would be basically everything you can ask with series and parallel springs. You're not going to have to do a combination network that is explicitly like a like a boundary statement. So just knowing what's the same, what's different, what gets stronger, what gets weaker. That's kind of everything for your networks of springs.